So in this video, we will be performing a von Neumann stability analysis to show theoretically that the limit of stability on the explicit differencing scheme used in part 2 is correct. So as you can see up here, I have our equation, our heat diffusion equation for Cartesian coordinates from part 1 written up here, and then we have solved it for t using just solving the partial differential equation. I'm not going to show all that in this video. It's not really important to the problem that we're trying to solve, and it would take way too long to do that. But yeah, that's what that is here, solve for t. And then right here we have our explicit differencing equation that we used in part 2 that we graphed and made a code for in part 2. And again, we need to remember that when we were at 0.5 seconds or greater, it became unstable and we had that really wacky graph. So what we're going to be doing in this video again is we're going to be performing von Neumann analysis to show that this is the correct value. So what we will want to do is plug in our t up here into this big differencing equation we got in part 2. But as you can see, these have j and n variables, whereas this does not. So we're going to have to solve this for t, j, and n. And again, from part 2, we know that our j values is dealing with our position. So we know that x is equal to delta x j from part 2. And then our n is based on time. So our little t up there is equal to the same thing, delta t times n. And now we can plug these in up here for our x and t and get our t, j, and n. So it will be equal to e to the I, k, and again, forgot to mention these k values in the equation we solved up here are constants. They're just based on our boundary conditions in the problem. So I, k, and then that would be delta x j, and then e to the negative alpha k squared, and then delta t n, like so. So now, as you can notice, we don't just have a t sub j comma n. We actually have these other two of j plus 1 and j minus 1. So we are going to have to solve for those as well, but it is not going to be that difficult. So I'm going to erase this little thing we had here, and then we will start with t sub j plus 1 comma n. And so obviously it will just be basically the same thing, but we will just have a j plus 1 here. And then this will all be the same. And so we can actually simplify this, and it's going to seem a little bit complicated, but once I write it down, you'll definitely understand it. So what we can do is we can actually distribute all this out into the j and plus 1. And what we will end up getting is that our t j plus 1 n will actually just be e I k delta x plus rt jn. And so why this is true is when you distribute this out, the I, k, you'll all just get it all multiplied by 1, and then this one multiplied by j, which is just our equation up here. Actually, this should not be a plus, it should just be multiplied, I'm pretty sure. And then now for our t j minus 1 m, that one will just be the same thing, but negative here, because we are multiplying by negative 1. So negative ik delta x, and then our t sub j comma n. So now we can substitute these in here and here, and rewrite this whole equation. So I'm going to erase this. And this. And we will rewrite the equation here. I actually really just want to rewrite it up here, so I'm just remember what these are. R plus 1 minus 2r. So we have r delta x, and so we can just factor out the t sub j comma n, as you can see what I did here. So we factored that out of all the different equations there. I'm also going to erase this as well, and then we will. So now what you can notice is we have these e to the negative I and e to the I portions of this function, and we can use Euler's formula, which says that e to the I x is equal to cosine x plus I sine x. And for our situation here, we also have the negative version of this, so e to the negative ix. And then what we can do is just flip this to a negative. And so now we have substitutions that we can put in here, and since these are added together, we can just add these as well. And that means that these will cancel, and we will just be left with 2 cosine x. And again, this x value here is actually just everything that is in here other than the I. So for us, it'll be k delta x. And that's what this x will be here. So now we can substitute this in. And we will get, let me erase this better. We will get, again, the same over here. And we still have that 1 minus 2r. But then now we have 2r cosine of our k delta x. Like that. So the key to this von Neumann stability analysis is this portion of the equation right here. And what we're going to want is that to be less than 1. And that's because if it is greater than 1, this will be increasing very, very quickly. And also if it is really, really small, this will be decreasing very, very quickly. And that's what we saw when we had 0.5 with that graph that just kept going up and down and up and down. So again, we need the absolute value of this portion of this equation to be less than 1. So now I'm just going to erase all this, and we will want just this equation. And we're going to set it in an inequality. So we want it greater than or equal to -1. And then less than or equal to 1. And now what we can do is we can subtract 1 from both sides of this, or I guess technically all 3 sides of this inequality. So we will have -2, and then we can actually factor out this 2r, and we will have cosine k delta x minus 1, and then 0 over here. So now, as you can see here, this cosine right here is always going to be less than or equal to 1. So that means that this portion will always be negative. And then our r here will always be positive, because we know that formula is just made up of a bunch of constants that are positive. So knowing that, this whole thing will always be negative, so it'll always be less than or equal to 0, so we can get rid of this part. And then now what we can do is we can divide by 2 on both sides, and then we can also flip the inequality and divide by our cosine part right here as well. So again, what I'm going to be doing is dividing by 2 and this part here, so we get r isolated, and then flipping the sign as well. So it'll be like that, and then r by itself on this side, and then we have 1 over 1 minus cosine k delta x. And I kind of didn't give myself enough space over here. So we'll have 1 over 1 minus cosine k delta x. And again, what I did was divide by 2, divide by this, and flip the inequality. So now let's just think about what this cosine term could be. So again, at its highest value, cosine of x could be 1. And if we plug that into here, we would get 0 on the bottom here, and we would need our r to be less than or equal to infinity, which doesn't make much sense. So if we think about the lower bound, -1, so 1 minus -1 will be 2. So then we get that 1/2 is, or that our value has to be less than or equal to 1/2. And that makes a lot of sense with what we saw in the last video, where we had our delta t value, that when it got to 0.5, it was unstable. So how that makes sense with our von Neumann analysis is that, again, this r is equal to delta t over delta x squared and alpha up here as well. And this alpha and delta x squared were both 1. So really our r is equal to our delta t. And that's why we noticed that at 1/2 our graph became all wacky and it was unstable.